Hi, everybody. Today we're going to talk about Wheatstone bridges. A Wheatstone bridge is a resistor network that allows us to use a voltage differential between 2 points to help us accurately measure resistances. Okay, so we're going to go through several examples today. And what we're looking at is we want to get the voltage of AB, so VAB. So first we need to find VA. And this here is a voltage divider network. So VA is essentially going to be equal to VR2. So VA is equal to R2 over R1 plus R2 times E. And then VB is also VR4 between B and ground. So it'll be R4 over R3 plus R4 times E. And that'll give us VB. And then VAB, the voltage between the 2 points, is equal to VA minus VB. So like I said, we're going to go through several examples. This is used for using very accurate measurements to detect small resistances in a circuit. And we're talking about thermistors, strain gauges, photoresistors. So we'll show you some examples of how those are implemented. And this is also used to figure out a unknown resistance. Okay, so to figure out an unknown resistance, what happens is we would tune the circuit until VAB was equal to 0. Okay, so when VAB is equal to 0, that means that VA and VB are the same. Okay, and since we know R1 and we know R2, and R3 is going to be adjusted until we get 0 here. And once we know these three, we can figure out R4. Okay, so this is to detect an unknown resistance, and we'll go through an example of that. Okay, so our first example is we have a, we're going to go to Multisim here. There we go. So now we have a simple Wheatstone bridge. Okay, so what we have is R1 is 4K, R2 is 3K, R3 is 4K, and R4 is 1K. So we have VA, which is also VR2, we have 5.142 volts. And for VB, we have 2.4 volts. Okay? And so we have the difference here in VAB. All right, so the way we get that is we're going to switch back to our camera. So we have that circuit right here. So VA is equal to R2 over R1 plus R2 times E. And that works out to 3K over 7K times 12. All right, so there we get 5.143 volts. Okay, we get 5.143 volts over here. Now for VB, which is this voltage, it is R4 over the sum of R3 plus R4 times E. So it is R4 over R3 plus R4 times E, which gives us 1K over 5K times 12, okay? Which is 2.4 volts. And then we told you earlier that VAB is equal to VA minus VB, which works out to 5.143 minus 2.4. So we get 2.743 volts. So that is how we calculate what ends up there. So here we have 5.143 volts. At point B, we have 2.4 volts. And then between A and B, we have 2.743 volts. Okay, that is calculated. So if we go back to Multisim, so we have 2.741 volts. So we carry our decimal places, and Multisim has a little bit of inaccuracy built into it. So, but that is how we calculate it, okay? So that part there is very simple. It's simple voltage divider formula, and that gets us there. So now, if we were to use a Wheatstone bridge to determine this unknown resistance, okay, we have an unknown resistance here. So what we do is we have fixed R1 and R2, and then we have a variable resistance at R3. So we're going to keep adjusting R3 until VAB is 0, okay? So we have 29, so we're moving away, so let's go backwards. 46 millivolts, 29 millivolts, 11 millivolts, negative 6.447 millivolts, and then we're moving away again 24. So let's go back. So there we are. That's about as close to 0 as we're going to get on this thing. So we have, we know R1, we know R2, now we know R3, it's 82.5% of 2K. So now we can calculate R4, okay, because we know VA is equal to VB. All right, we have 1.142, 1.148. Again, if we're a little more accurate, but let's calculate with what we have. All right, so we're going to bring up, we're going to go back to our sheet, and I just want to show you how we're going to come up with the math that we do. So we know when VAB is equal to 0, when VAB is equal to 0, we know that VA is equal to VB. So if VA is equal to VB, the formula for VA, R2 over R1 plus R2 times E, is equal to the formula for VB, which is R4 over R3 plus R4 times E. Okay, so in one swoop, we can cancel out the E's on each side, and I cross multiply, so I have R2 times R3 plus R4 is equal to R4 times R1 plus R2. So we end up with R2 R3 plus R2 R4 equals R4 R1 plus R4 R2. Now we can calculate, eliminate R2 R4 on both sides. Okay, we can eliminate that. So now we have R2 R3 is equal to R4 R1. And now if we solve for R4, it's R2 R3 over R1. So that's what we get there. All right. So if we bring up the circuit that we just worked on, this is what we have. Okay. So E is 12 volts here. Now we know R3 is 82.5% of 2K. All right. So that's equal to 0.825 times 2000. That's equal to 1.65K. All right, so we know from before, we know that VA is equal to VB, okay? And we know that VAB is equal, we're gonna say almost 0. We can't say it was equal to 0, so we'll also say that these are approximate. Okay, so now, if you remember from before, if we want to calculate this resistance, it is R4 is equal to R2 times R3 over R1, which is R2 is 3K, R3 is 1.65K over R1, which is 4K. And that gives us, I know the suspense is killing you, $1.2375K. All right, and that is calculated. 1.2375K is that unknown resistance. So if we go back to Multisim, and we reveal that resistor, 1.24K. All right, so we had 1.2375 that we calculated, and the hidden value was 1.24. So that is how you would use a Wheatstone bridge to determine an unknown resistance. Okay, and that is a common use for it. So some other examples, we can also use a Wheatstone bridge if we have an input here that can be it could be a thermistor for temperature, it could be a photoresistor for light, it can be a strain gauge. Okay, so if you want to learn more about strain gauges, you can go look those up. But a strain gauge is when you put a certain amount of stress or strain on the strip, the resistance of it changes. All right, and so what we do is we put that input here as R4. And what happens now is we use the voltage difference that we measure between A and B to tell us how much resistance is here. So you would actually make a table ahead of time. You would say this resistance equals, this VAB is equal to this much resistance in R4. And we're going to show you how that's acquired and used. But basically what happens is, as I just put a variable resistor here to emulate. So as, say, the level of light changes for a photoresistor, or as the temperature changes for a thermistor, or as the strain on the strain gauge changes, the resistance changes. And as the resistance changes, you'll see down here, VAB also changes. Okay, so VAB will constantly, turn this one on. There we go. So as we change the resistance on our input, the voltage changes. Okay, so now we could take that voltage and we could input it into other devices to help us determine what's going on here, whether it be temperature, whether it be photoresistor, and we have a few examples. All right, but if we keep changing this, then VAB changes, and the VAB can be read by another device and used for further processing. So here, we're going to stop this circuit. We're here now. I have what's called an analog to digital converter. Okay, so this will convert voltage levels to this particular one, an 8-bit binary number. Okay, it would be an 8-bit binary number. So what I have is, I'll be at 0 right now. An analog digital converter has a reference voltage, so we're going to use VA as our reference, and then VIN between 0 and the reference voltage will be represented by 256 levels of binary numbers. So if we start at 0, we have 0 volts here, our binary number is 0. As I add resistance to R4, which could be, again, a thermistor, a photoresistor, a strain gauge, anything like that, you'll see that the binary number is counting up. The binary number is increasing. Okay, now that binary number can be read in by a microcontroller. And now what it can do is it could take that value and make whatever adjustments are necessary. For instance, if we were using some kind of temperature sensor, then we would use this. You would program your controller to read the temperature, and if you wanted something kept at a certain temperature, if the input temperature is higher than expected, and then you run a cool down process. If your input temperature is lower than you want, then you would run some kind of process to heat up. Okay, so basically we are now converting the resistance of R4 into a digital value, and this can now be used by a microcontroller. So you're going to be learning more about analog to digital converters as the program progresses in different courses, but for now it's just a brief introduction that the voltage between 0 and Vref is represented, is cut up into 256 levels and represented by whatever our input voltage is. Okay, so instead of measuring VA is now the reference voltage and VB is the input. But suppose this was a light sensor or a temperature sensor, and you needed to make some adjustments. You need to calibrate it because something was a little bit off, because you do have inaccuracies in resistors. How do we do that? Well, our voltage right now, our reference voltage is set to R2. It's fixed, okay? But what we can do is, if we'll go to the next simulation, I put an adjustable variable resistor in this little network down here for R2. So what we can do now is we can adjust our reference voltage. Right now it's 2.303, but I want to turn it up a little bit. I want to turn it down a little bit, sorry, because I think our temperature is off by a little bit. So I've got it now at 2.02. So now I have a proper calibration for us at, I'm going to take this here. So what's happening now is, as I move up, I get my digital values, okay? I get my digital values, but now I am over. I'm over now, okay? So those are adjustments you make in your design. Okay, let me turn this up again. I'm gonna have this at 2 volts. So what I'm doing now is at 2.2 volts instead of 2.4 in the previous. So what I'm doing now is I'm adjusting, and my levels are a little bit different because they've been calibrated. And what I did on this circuit, I still have my binary bits to show through LEDs, but I also added some 7-segment displays to display the hex value. Okay, and as you know from your digital course, 1010, 0101 is A5. And if we want to move this over, now I have D9, so I just decided to just represent it a different way for you. But those 8 bits would be read by a microcontroller with a program running, and so that would be the input, and then it would have whatever process to control whatever output it controls. Okay, so that's one example where we are reading VAB and taking the difference between the two and converting it to a binary number. All right, another example is, I'll stop that and I'll move over. So what I've done here now is I've taken our Wheatstone Bridge, okay? And now I've put the variable on the bottom left. So I've taken VA and VB and plugged them into a comparator. Okay, so this comparator now, you're gonna learn more about those in electronics, and op amps. That comparator is going to take the inputs at the positive and negative input. And what it does is, if the positive input is greater than the negative input, it's going to put a 1 out on pin 7. If the negative input is greater than the positive input, then it'll put a 0 out, okay? And what I've done here is, when there's a 1, I have it energizing the gate of a TRIAC, and you're gonna learn more about TRIACs, but basically this TRIAC acts like a switch. So when I put a small amount of voltage into the gate, this TRIAC will allow this 120 volt circuit to operate. So this is going to simulate a photoresistor. And a photoresistor, as it gets darker, the resistance goes up, okay? As it gets darker, the resistance goes up. So what happens now is, on a photoresistor, right now it's the middle of the day, voltage is 0, so negative is greater than positive input on the comparator, which means we have a 0, so nothing's happening here. So it's still light out, So we do not need this light to be activated outside. But as it gets darker, we have, you see the input, R6, the photoresistor, is getting higher, and that voltage is getting higher. Okay? The voltage is getting higher. So what happens now is when we hit a point where that exceeds VB, okay, where VA exceeds VB, this is VA, this is VB, 2.51, 2.507, so we still have a 0 on here. So watch what happens when I go above that. Now, the comparator is putting out a 1, turns on the TRIAC, and this circuit here is allowed to flow. Okay? And it stays like that all night. So resistance keeps going up, and then when the sun comes up, now the resistance is going down on the photoresistor, and eventually the light will go off. Okay, that is a very simple, a light that goes on when it's dark out. Okay, so what if we want that light to go on earlier? So not right when it gets night, but actually when it starts getting dusk. Okay, or we want it on much later when it's really dark, not just 8 o'clock in the middle of the summer dark. So what happens? So what we do now is that same circuit. I'm going to go to the next one. I put an adjustment here. So what I've done now is I've adjusted, or I'm able to adjust the threshold voltage of when this goes on. Okay, so we're going to say now this is 1.732. All right, or it's at 2.633, sorry. So now let's turn this down a little bit. So now what we've done is we've told our circuit that we want it to go on earlier. We want it to go on earlier. Okay, so in the previous circuit, we have our light going on when we were at 275 ohms. So when this was 275 ohms, 55% of 500, our light outside went on. Okay, but suppose I want to change that. I want it to go on earlier. So what I would do is, go back to this one, I would adjust this. So let's turn it down to, turn this on. Okay, so I turn it down to 2.26. So let's see when the light goes on now. I use B to control this one. Okay, so now the light is on. Let's see if it goes on a little earlier. Nope. So now the light went on at 45% of 500. So now it goes on at 225 ohms. So we could keep adjusting that, all right? So those are ways that we can acquire the voltage between A and B and use them in different ways. So what we showed you today was using a comparator and using an analog to digital converter. But your question might be, why don't we just use this value, period? Why not just use that value in a simple little circuit and like here and just let it roll? The problem is, as we've learned, that heat changes the resistivity of different devices. So what happens now is it will change the resistivity of all these devices so we're still able to stay accurate. Okay, so that's a big thing. So it's big that, one, you can use this. You can use it to do what you need, but you can also set your circuit up that the entire circuit will adjust with different changes in the environment, but you can also make a circuit where you have ways of adjusting and calibrating what you're reading at VAB. Okay, so by adding another variable resistor into the network with our thermistor, our photoresistor, our strain gauge, or whatever, you can keep your circuit as accurate as possible. Okay, so today you learned about the Wheatstone Bridge. You learned about an analog digital converter, just an introduction. You learned about a comparator, just an introduction. You'll get more as the program goes. And you learned about a TRIAC. All right, so we covered a lot of ground here. I hope you found it useful, and we will see you next time.